Good morning. This meeting is being recorded. And so today we're going to finish off chapter 2, and that sets us up to be ready to complete our first chapter exam by Sunday of this week. And that will be a date of the 27th, I do believe that is. And so I have prepared for you a little study guide.
You have to catch about all night.
And if you go to the news item on the home page and just click on that link, then the study guide will appear. And so this little study guide just lets you know what things, what topics, concepts, types of calculations that you should focus on in your study. Now, the exam is going to be taken, of course, at home on your computer via eLearn and Connect. And so when you're ready to take your exam, make sure you're in a quiet place where you can focus. You will have 75 minutes to complete the exam. So once you start the exam, you have to finish it within that 75-minute time frame. So if you go to the course content tab at eLearn, you'll find the link to the exam. Go through your table of contents and just scroll all the way down to tests. And just click on tests and you'll see your first chapter exam. Click on it and it'll take you to Connect. And so when you're ready to take your exam, being that you only have 75 minutes, the best thing that you would want to make sure that you do is that you're organized. You can use your notes for the exam. Okay, so, but it's important that your notes are organized. And so, however you want to organize, I advise you to print out your notes that you've been annotating during lecture and hole punch them and put them in a 3-ring binder. That way they're organized. You can use the different little sticky notes, sticky flags or whatever to mark certain pages. You know, if you want to know where the ppm to percent conversion notes and conversion factors are in your notes, I would put a sticky note there. And so I know, hey, I can quickly get to that page if I need to quickly refer to the conversion factor for converting between a percent and a part per million. You know, things of that nature, being organized so you're not wasting time looking for things, okay? So it is open notes, but make sure your notes are organized so you don't waste time. So just go through this little list as you're studying. And if you understand all of these concepts, then you'll be in good shape for the exam. And so how to best prepare for the exam, go through this study guide. Of course, study your notes and study over those problems that we work during the lecture. Also go back and study your chapter quizzes for chapters 1 and 2. You'll definitely see problems like the ones that were in your quizzes on the exam. That's an absolute. And so those would be my pieces of advice for how to prepare for the exam. Go back through your notes. And as you're going through your notes, go through these lists of things, making sure you understand everything that's in the study guide list. Study over the problems that we did in class, in lecture. And then go back over your chapter 1 and chapter 2 quizzes and study over those problems. And then you will be in good shape for the first chapter exam. So again, this little study guide, you can find it on the eLearn course homepage in this news item. Just click on first chapter exam study guide, and it'll take you to the PDF. And you can download that PDF file. And you can also find this under the course content tab as well, right underneath chapter 2. There's the study guide there again. So I've got it in 2 places. And also, I posted a news item with some math review videos. And so just click open a new window. And then you'll be taken to a list of different math review topic videos, things like significant figures, scientific notation, how to use a scientific calculator, unit conversions. So those are some very good videos. So if you're struggling with unit conversions, I would definitely advise you to watch those videos. Density is another one that I would watch. We're going to talk about density today. And so definitely check out the math videos if you're struggling with unit conversions and scientific notation, and also scientific calculator use. I think all of those would be good videos to review. Okay. So as you're studying, if you have any questions, if you want to have a one-on-one Teams meeting with me anytime between now and Sunday, please just send me an email. Let me know what day, what time you want to meet with me, and I'll set up a Teams meeting. If a group of you want to schedule a group Teams meeting, like the members of your group that you do work problems with in class, if you want to schedule a group meeting with me, just let me know. You can send me a message via email, or you can send me a message via Teams by clicking on the chat button on the left-hand side. And you can send me a message via Teams anytime, any day, anytime, day or night, just by going into Teams and clicking on that little chat link. And then you can send me a message. I prefer eLearn email. And just let me know what day, what time you want to meet, and I'll do everything I can to accommodate you. So we talked about limiting reactant on Monday, and we said that the limiting reactant is the reactant that runs out, that gets used up during a chemical reaction. The other reactant will be the excess reactant, because some of that reactant is left over. And so I wanted to clarify this little modeling sulfur dioxide formation little piece here. And the first picture on the left is a correct representation of how sulfur dioxide is formed from sulfur and oxygen. And the picture on the right, picture B, is incorrect. What makes picture A correct is that it's showing the molecular forms of sulfur and oxygen. Whereas in picture B, it's showing the elemental forms. Noted that this is a sulfur, the little yellow circle, and the red circle is oxygen. Both of these elements exist not in elemental form in nature, but as allotropes, as we discussed in a previous lecture. Oxygen exists as a diatomic molecule or molecular element, O2, whereas sulfur is usually found in an allotropic form, either S5, S6, S7, or S8, S8 being the most abundant, the most popular form. So that's why panel A is the correct representation and panel B is the incorrect representation, because panel A shows those reactants in molecular form. And so in part B, in predicting the products of either SO2 or SO3, S8 will combine with the 4 oxygen molecules to form SO2. And in balancing the equation, so I'm going to show it unbalanced, in forming SO2, and if we know that we have 4 of the oxygen molecules available to react with 1 of the S8s, so we'll just put a 1 there for good measure. Then when we form the SO2, if we have 8 oxygens on the left to have 8 on the right, we put a 4 in front of SO2. But that just gives us 4 sulfurs on the right. So there's an additional 4 sulfurs that will be our additional product. And so this would be the excess sulfur that didn't react with the oxygens. So therefore, in this representation, sulfur then is the excess reactant, and oxygen is the limiting reactant. All of the oxygen gets used up. We have 8 oxygen atoms as reactants, and we have 8 oxygen atoms as products here with the SO2. So all of the oxygen atoms, all 8 of them, were used during the reaction, whereas only 4 of the sulfurs were used to be converted into SO2. The other 4 sulfurs were unreacted. And then in forming SO3, you also form SO2. So you can make 2 SO3 molecules, 1 SO2, and then you have 5 sulfurs left over. So in both reactions, in forming SO2 and in forming SO3 as well as SO2, you have excess sulfur left over. So does all the oxygen atoms react? Yes. And so therefore, sulfur is your excess reactant. Oxygen is the limiting. And so what you have as leftover sulfur is in the elemental form of sulfur, but you don't have any elemental oxygen atoms left over. So therefore, all of the oxygen did get used up. And so after the reactions are complete, unreacted sulfur atoms are left over. Yes, that is true. There are 4 sulfur atoms left over in the first reaction, and then 5 sulfur atoms left over in the second reaction. And so therefore, sulfur is the excess reactant because you have elemental sulfur as the product. And so in continuing to talk about limiting reactants and the fact that we have an exam coming up, our first chapter exam, I do recall 1 or 2 students asking me throughout the semester, will we ever have any bonus opportunities? And I answered yes to that. I will, throughout the semester, provide maybe 2 to 3 different bonus opportunities. I would try to provide you 1 bonus opportunity per test, per regular test that we have during the semester. So I'm going to provide you a 10-point bonus opportunity. Those 10 points you'll be able to add to your first chapter exam. And the bonus opportunity is going to be based on the concept of limiting reactant. So what I'm going to do today is go through with you a certain scenario. And then for the bonus assignment, you're going to be working with a similar scenario that we're going to go through today in lecture. And so based on what we go through in lecture, you use that as your guide to complete the bonus assignment, which will look a lot like this little exercise here that we're about to go through. So if you would like to, after class, to follow this link to watch the YouTube video in which I obtained this data, then you can do so. There'll be a similar video that you'll watch to complete the bonus assignment. I'll place the bonus assignment in eLearn, and I will place it under the Activities tab and Assessments. And so right now I haven't created any, but I'm going to create. I'll go ahead and create it now. It's going to be, I'll call it the limiting reactant bonus assignment or bonus assessment. And it's going to be based on the synthesis of aspirin. So the video that I gave you a link to actually shows a chemist synthesizing aspirin in the lab. And so once I get the questions ready for this bonus assessment, I will send you an email to let you know it's ready. I'll have it finished probably by Saturday, and then I'll give you a few days to complete it. And so right now you see the little eye with a line in it. So right now this is hidden, but you'll be able to see it once I have the questions finished. So you'll be able to add up to, and you'll be able to get partial credit. There'll be a few different questions. And so the questions will be worth between 1 and 3 points each, giving you a total of 10 possible points. And so you will have the opportunity to increase your letter grade on the first exam by 10 points. And so therefore an increase by a letter grade. And so the video shows a scientist synthesizing aspirin in the chemistry laboratory. And to synthesize aspirin, you need 2 reactants and a catalyst. And so the 2 reactants that you need are salicylic acid. So that's its structure. It's on a molecular level. Here is its representation in the symbolic level, showing you the formula. Salicylic acid has a molar mass of 138.12 grams per mole. So remember when we did percent composition of an element in a mineral, like bauxite, for example, or for an aluminate like Al2O3, what's the percentage aluminum in Al2O3? Well, in order to do that, we need to know the atomic mass for the aluminum and then multiply that by however many number of aluminums that were in the formula for this aluminate, and then calculate the same for the oxygens that are in the formula. And then when you add all those numbers together, you get the molar mass for that compound. And so that's what the molar mass represents for a compound. It's the sum of the atomic masses for all of the elements that make up that compound. And for salicylic acid, you have 7 carbons, 6 hydrogens, and 3 oxygens. So that's how that 138.12 was calculated. And then the other reactant is acetic anhydride, having the formula C4H6O3, and therefore a molar mass of 102.09 grams per mole. Now, salicylic acid is a solid at room temperature, but acetic anhydride is a liquid at room temperature. And so acetic anhydride has a density. That D stands for density. The density of acetic anhydride is 1.08 grams per milliliter. 1.08 grams per milliliter. And so density is equal to the mass of a substance per unit volume. And for liquids like acetic anhydride, the mass unit is going to be grams. The volume unit is going to be milliliters. Those are the most popular units to use for density for liquids. And so the density having a unit of grams per milliliter. And then you have to use an acid as your catalyst to make this reaction go fast. Without the catalyst, it would go too slow. And then you get your two products. The first product, that's your aspirin. That's the common name, aspirin. The scientific or the systematic name would be acetyl salicylic acid. It has a formula C9H8O4, and it has a molar mass of 180.16 grams per mole, and it is, as we know, a solid at room temperature. And then the other product is considered a side product, acetic acid, with the formula C2H4O2. It is a liquid at room temperature with a molar mass of 60.05 grams per mole and a density of 1.05 grams per milliliter. And so we talked about molar mass being the number of grams of a substance per mole of that substance. Note the word per that I used. That should remind you of a fraction. Density being the number of grams of a substance per milliliter of that substance. And so we also said that fractions, conversion factors are fractions. And so these are two new conversion factors that we now get to work with, density and molar mass. So we can convert between grams and milliliters if we know the density of a substance. We can interconvert between grams and moles of a substance if we know the molar mass of that substance. So we can convert a gram to a mole by dividing by the molar mass. So take the grams, divide those grams by the molar mass, and you will have converted those grams to moles. And of course, you can go in the opposite direction. You can convert a mole to a gram by multiplying by the molar mass. Then also, you can take a gram and convert it to a milliliter. By dividing by the density. And then again, you can go in the opposite direction. You can take volume and convert it to grams, which is mass, by multiplying by density. So we can use density and molar mass as conversion factors. So if we're in the laboratory and we want to make some aspirin, we're going to weigh out 3 grams of our salicylic acid reactant. it's a solid at room temperature, so we have to weigh out an amount that's in mass units. And our balances in the lab are in grams. The acetic anhydride is a liquid. So for liquids, we measure volume. So we measure out 6 milliliters of the acetic anhydride. So our first step is to calculate the grams of acetic anhydride used. Well, we know how many milliliters used. So if density is mass divided by volume, we can calculate the mass, like our flow chart says, by taking the volume in milliliters and multiplying the milliliters times the density. So volume times density, our volume is 6 milliliters, and the density of acetic anhydride is 1.08 grams per milliliter. The milliliters cancel. So note how the unit that I wanted, grams, is in the numerator. The unit that I needed to cancel out, the milliliters, those are in the denominator. So we're using the same technique for converting units that we learned previously. So 6 times 1.08 is 6.48 grams. The next calculation is called the theoretical yield in grams of aspirin, our product. So based on using 6.8 grams of acetic anhydride and 3 grams of the salicylic acid, how much of our product aspirin should we be making? So if we look at this balanced chemical reaction, so this is why having a balanced chemical reaction is important, so that you can calculate the theoretical yield, which is predicting how much product you're going to make. And so with our balanced chemical reaction, we notice that there aren't any coefficients in front of either of our reactants or products. And so we said that when there's not a coefficient in front of a reactant or a product in a balanced chemical reaction, then it's understood to be 1. So what this is saying is that for every 1 mole of salicylic acid and 1 mole of acetic anhydride that we react together, we're going to produce 1 mole of our aspirin and 1 mole of acetic acid. Those are our 2 products. So looking at your balanced chemical reaction, you can be able to get a mole ratio of reactants to products. And for this balanced reaction, it's a 1-to-1 ratio. So to answer our second question, knowing that we have a 1-to-1 mole ratio of each reactant to each product, we can calculate the theoretical yield. So for our salicylic acid, and also we're going to be able to determine which reactant is our limiting reactant and which reactant is our excess reactant by calculating the theoretical yield. So we're going to calculate the theoretical yield of our aspirin based on each reactant. We have 2 reactants, the salicylic acid and the acetic anhydride. So based on the salicylic acid, we use 3 grams of it, and I'm going to abbreviate salicylic acid SA. And then we look at the molar mass for salicylic acid is 138.12 grams per mole. So we can convert the first step is convert the grams of each reactant to moles. That's our first step. And to convert grams to moles, we divide by the molar mass of that reactant. And so we'll do that calculation. So 3 divided by 138.12. So 3 grams of salicylic acid is equivalent to 2.17 times 10 to the negative 2 moles of salicylic acid. And then our balanced equation tells us that for every 1 mole of salicylic acid, we produce 1 mole of aspirin. So based on the salicylic acid, we make 2.17 times 10 to the negative 2 moles of aspirin. And now we do the same type of calculation for the acetic anhydride. We use 6.48 grams of acetic anhydride. I'm going to call it AA for short. And look at its molar mass, 102.09. So the grams cancel. So we calculate how many moles of acetic anhydride we used. 6.48 divided by 102.09. And that gives us 6.35 times 10 to the negative 2. And again, because for every 1 mole of acetic anhydride that you react, you're producing 1 mole of aspirin. Based on acetic anhydride, you're making 6.35 times 10 to the negative 2 moles of aspirin. And so we have to now pick, well, which one of these is our theoretical yield? Are we going to make 2.17 times 10 to the negative 2 moles of aspirin? Or are we going to make 6.35 times 10 to the negative 2 moles of aspirin? Well, the answer is always the smallest. The smallest of the two values will always be your theoretical yield. So our theoretical yield is going to be based on the amount of salicylic acid that we use. So therefore, based on that, which one of these reactants do you think is the limiting reactant? Salicylic acid or acetic anhydride?
Is it the salicylic acid?
Very good. Because it limits the amount of product, aspirin, that we can produce So salicylic acid is our limiting reactant. And so now that we know how many moles of aspirin that we're going to produce, we can take the 2.17 times 10 to the negative 2 moles of aspirin, and we can convert it into grams. So this is based on the salicylic acid. Aspirin has a molar mass of 180.16 grams per mole. So we're multiplying the moles times the molar mass, just like our flow chart says, to get grams from moles. So we're going in this direction. We multiply the moles by the molar mass to get grams. That gives us 3.91 grams of aspirin based on the salicylic acid. Based on the acetic anhydride, we'll be making 11.4 grams of aspirin. So even in converting it to grams from moles, we clearly see that salicylic acid is our limiting reactant because it's going to produce the smallest amount of product. It's going to limit the amount of product that we can make. Okay? And so we answered that question. Salicylic acid is limiting. And so let's say if the scientist actually made 3.1 grams of aspirin. So theoretically, based on the numbers, based on what the scientists measured out and used as reactants, 3 grams of the salicylic acid, 6.48 grams of the acetic anhydride, she should have theoretically made 3.91 grams of aspirin, but she only made 3.1 grams. Why? Because she's not perfect. You're always going to lose a little bit. You may not have gotten all of the liquid out of the graduated cylinder, the acetic anhydride, when you poured it in with the salicylic acid. So all those little experimental little errors comes in. And so you'll never get 100% yield. So we weren't expecting her to make 3.91 grams because she's not perfect. But you do want your percent yield to be high. So therefore, how do you calculate the percent yield? It's going to be equal to the actual yield, what you actually make in the lab, divided by what you should make theoretically, the theoretical yield, times 100. So this scientist's percent yield is 3.1 grams divided by the theoretical yield of 3.91 grams. So she did pretty good. If your percent yield is 90% or greater, then you had a very good experiment. So her percent yield is 79.5%. Not too bad. So for your bonus assignment, you're going to be given a scenario very similar to this one. You're going to be dealing with the same compounds, making aspirin, using salicylic acid, acetic anhydride. Only thing that will be different are these numbers. You're just going to be working with different numbers, but the same compound, same reaction. And then there'll be about 3 or 4 questions that you'll have to answer after you watch the video of the scientist, and it'll be a different scientist than this video. You'll watch the video of the scientist making the aspirin. You'll record the data. And then you'll answer questions similar to these. Okay. Any questions about that? Bonus assignment. And I'll have it posted in eLearn probably around Saturday. And then it'll be up for a few days. You'll have until probably Wednesday of next week to get it finished. Okay. So it'll be up from Saturday through Wednesday of next week. And you can pick any time during that time period to get it finished. Gavin, I'm going to put it due probably about Wednesday of next week. Okay. So it won't be due until after your first chapter exam is due. So you can work on it after you finish your exam. These types of calculations that we went over today, the only one that you're going to be responsible for on the first chapter exam is this density formula. I do believe there's a density calculation, just like this one here, the very first one, that I used to take the volume and the density and calculate mass. There will be a question on the exam dealing with this calculation, but there won't be any theoretical yield or percent yield calculations on the exam, but there will be a density calculation on the exam. Your exam has 40 questions and you have 75 minutes. Not all of the questions are calculation based. You'll have some questions like asking you identify which one of these is a compound, questions that you should be able to answer in a matter of seconds. So not all the questions are calculations. You may be asked something like, what does the color orange mean as far as the air quality index? Questions like that are theoretical questions that if you've studied your notes and if you've read the chapter, that you should be able to answer in a matter of seconds. Which one of these is an air pollutant that affects the lungs, or questions like that don't require calculations. You'll have a lot of those, and then there will be, of course, questions that require calculations. I haven't done a ratio, but I could do that, and I'll send you that in an email. I'll take a look at the test and see how many of the 40 questions are actual calculation questions. Because, of course, the calculation questions should take you a little bit more time than the non-calculation questions. So I'll be able to answer that for you a little bit later, and I'll send it in an email to let you know how many of the 40 are actually calculation questions. Any other good questions for me? Madison, if you want to get the recorded lectures, if you click on the Teams button on the left-hand side of your screen, it should take you to General, and you see Posts. And then if you scroll down where it says Posts, you should see the recorded lectures. And those are good for 20 days. After 20 days, they automatically expire. Okay. And so one thing I was going to ask anyone that want to be able to do this, if I don't announce at the beginning of the lecture, this lecture is being recorded, that means that I forgot to hit the record button. So if you don't hear me say that at the beginning of the lecture, just send me through the chat thing, or unmute yourself and just speak freely and say, hey, Dr. Cook, are you recording this? So just remind me feel free to remind me at the beginning of the lecture if you don't hear me say that it's being recorded, because I have to disclose that to you. I can't record the lecture because of privacy rights. I have to let you know I'm recording the lecture. So if I don't tell you that I'm recording the lecture, that means I'm not. That means I forgot to press the button. And when I do press the button, there's this big thing that comes on my screen. You are being recorded. Make sure you disclose this information. So if I don't disclose that information, it's because I didn't hit the button. So make sure someone, if you don't hear me announce it, that you remind me, hey, could you record this, please? I would appreciate that. And so we know that combustion reactions involve the burning of a substance in the presence of oxygen with some type of spark or ignition being the catalyst. And we've also talked about combustion reactions, and most combustion reactions involves burning fossil-based fuels like octane, which is the major component of the gasoline that we put in our cars. And we talked about how it's important for these hydrocarbons to completely combust because the products are CO2, which is a greenhouse gas, and that's a problem, and water. But when we have incomplete combustion, that means there isn't enough oxygen available, and you start producing carbon monoxide, which is an air pollutant and very poisonous. And so you want to make sure there's very little carbon monoxide being produced by your engine in your automobile. And so there's always going to be a small amount of carbon monoxide being produced. But large amounts of carbon monoxide being produced by your automobile engine is a sign that your automobile engine is not performing efficiently. That may mean you just simply may need a tune-up. And so most states have vehicle emissions requirements for vehicles that are a certain age. All brand new vehicles are, of course, going to meet the emission quality standards set by the EPA. But as your vehicle ages, it may not meet the EPA standards. And so this is a copy of an emissions report. And it shows the amount of certain compounds that are generated from the exhaust of an automobile, things like carbon dioxide, nitric oxides, and the dangerous carbon monoxide. Both carbon monoxide and the nitrogen oxides, NO and NO2, those are all air pollutants. And so the green line that you see is the standard. And so what the graph shows you is how many seconds on the x-axis, and then the miles per hour that the car is going are on the right y-axis, and then the left y-axis shows you the grams per mile of this pollutant that get generated. And so you can see that as far as carbon monoxide, after the engine's been running for 160 seconds or greater, you start to exceed the EPA standards. And the same thing for the nitrogen oxides. Once you pass the 160-second mark, then that vehicle starts to not pass the standard regulations for that air pollutant. And so these emission tests will let the technicians know if the vehicle is operating properly or if it's exhibiting carbon monoxide, which is an incomplete combustion product, which could mean that the car just needs to tune up. And so we said that carbon monoxide is an air pollutant, and we talked about how it can be caused by an inefficiently performing automobile engine. And there are also some direct sources of air pollutants, like sulfur trioxide, SO3. It's called a secondary air pollutant because it's formed from another air pollutant, SO2, sulfur dioxide. The main way that sulfur gets in our atmosphere is through burning coal. But also some natural sources are volcanic eruptions. So whenever there's a volcanic eruption in a state or a country, for that matter, the levels of sulfur in the air will go up. And the reason why sulfur is so dangerous in the atmosphere, because it will react with the oxygen in the air and form sulfur dioxide, SO2. And then the SO2 will go on and react with more oxygen in the air and form a second pollutant, sulfur trioxide. So that's why it's called a secondary pollutant, because it's formed from a primary pollutant. And then SO3, the secondary pollutant, goes on to cause another problem. It reacts with water vapor in the air to form sulfuric acid. And sulfuric acid gets trapped in clouds, and then when it rains, the sulfuric acid falls to the earth with the rain, and that's what we call acid rain. And so since 1985, the EPA's standards to reduce sulfur trioxides and SO2s from forming in the atmosphere has been good. There's been a 55% reduction, and that means there's a reduction in the acid rain problem, because acid rain affects aquatic life, it affects the trees, and of course it affects our marble and other limestone based statues and monuments. It causes them to degrade at a much faster rate because the acids will react with the limestone. And then we talked about carbon monoxide already. Its main sources from automobiles and incomplete combustion of hydrocarbons. And then the nitrogen oxides, NO and NO2, they also form due to automobile engines. And the key thing about the automobile engine is that, of course, it gets very hot. So under those hot conditions inside of an automobile engine, two things that we see as normal and harmless, and of course that we need to live, the nitrogen N2 and the oxygen O2 in the air, when that air is trapped inside that hot engine, those temperatures act as a catalyst that causes the nitrogen and the oxygen in the air to react with each other. And when they react with each other, they form nitrogen monoxide. And then the nitrogen monoxide goes on to react with the oxygen to form nitrogen dioxide, which of course is an air pollutant. And so that nitrogen dioxide comes out of the exhaust pipe of your automobile, and it pollutes the air, and that is what gives smog its brown color. And another way NO2 is produced is when nitrogen monoxide reacts with ground level ozone. And ozone is another air pollutant. And so when NO reacts with ozone that's in the atmosphere, more nitrogen dioxide gets produced. And there's a small percentage of ozone that is emitted from automobile exhaust as well. Another compound that's emitted from vehicle exhaust are called VOCs, volatile organic compounds. They're also involved in NO2 production, as shown by this reaction mechanism here. And there are 3 steps to this mechanism. that involves the VOCs reacting with a hydroxide radical to form intermediate compound A, which reacts with oxygen in step 2 to form intermediate compound 2, which goes on to react with NO to form the NO2 pollutant. So one thing that has helped to reduce the amount of nitrogen dioxide that's formed in the hot engines of a car and then that goes out of the tailpipe and pollutes the air, producing smog, are catalytic converters. Catalytic converters reduce the amount of carbon monoxide and the amount of nitrogen dioxide that is released into the atmosphere through automobile exhaust. What it will do, it will reduce the nitrogen dioxide back into nitrogen and oxygen gases once it exits the tailpipe. So instead of nitrogen dioxide exiting the tailpipe, you get nitrogen and oxygen. Because what the catalytic converter will do is trap the nitrogen dioxide and then catalyze the reverse reaction to reverse the NO2 back into nitrogen and oxygen. It'll do the same thing to the carbon monoxide. It will cause it to react with oxygen and therefore produce carbon dioxide that's released instead of carbon monoxide. And then finally, particulate matter. It comes from fireplaces and wood-burning stoves. I think wood-burning stoves is the main source of particulate matter, but also when we have bad wildfires like we have out west right now, that produces a lot of particulate matter. Also construction sites, diesel engines, and volcanic eruptions produce particulate matter. So those are some of the sources of particulate matter. And so you can go to the EPA's airnow.gov website, and you can put in a zip code, and you can get the air quality index information for any area that you choose, and you'll know whether or not there is a risk for particulate matter or ozone in the air for that particular location at that particular time. They update the site every hour on the hour. And what they found out by collecting the data over a period of time, that in Southern California, ozone concentrations peak around mid-afternoon, but they drop significantly overnight. That's because sunlight is needed to produce ozone from the VOCs that exit the automobile engines and those nitrogen oxides that exit the automobile engines. And so in the middle of the afternoon, you have high levels of ozone in Southern California. And so, and the reason why is because that mid-afternoon, the sun is at its most intense level. And having that intense sunlight helps to speed up the rate at which ozone, which is an air pollutant in the stratosphere where we live, it helps faster catalyze the production of ozone from these VOCs and nitrogen oxides. And so unlike nitrogen and sulfur oxides that are direct pollutants, ozone is another secondary pollutant because ozone is formed from nitrogen dioxide, which is the primary pollutant. So when you catalyze nitrogen dioxide with sunlight, you produce NO and O. Then the O, that's the atomic form of oxygen. The molecular form of oxygen is O2. So O is just the atomic form or the elemental form of oxygen, and it's very reactive. It doesn't hang around very long. It's going to quickly react with oxygen in the air and form ozone. And that's your secondary pollutant, formed from the primary pollutant, NO2. So we've been talking a lot about air pollution as it relates to outdoors. But what about indoor air pollution? Are you at risk from indoor air pollution? Well, we don't think about indoor air pollution a lot. Most of the time, if someone says air pollution, you're thinking about what's going on outside. But you also should be aware of things that may cause your indoor air to be polluted. And one of the main things that you can do to keep the air where you live, where you work, of course, safer is, of course, no smoking indoors. And then also be aware of the things that you use in your home, such as air fresheners and incense candles. Air fresheners and incense candles and all those things have chemicals in them. And you need to be aware of the chemicals that an incense candle contain to make sure there are no VOCs that may be hazardous. And you need to make sure that the area where you're burning those candles is well ventilated. Well ventilation is a must. And also paint. Paint contains VOCs. So if you're painting the inside of your house, just make sure the areas are well ventilated, because if not, those air pollutants can build up in your house and can be very dangerous to breathe. Some other indoor air pollutants that have been of concern lately also is radon. Radon is one of the noble gases in group 8A of the periodic table. And so electrical appliances and other electrical apparatus, they give off a certain amount of radon naturally. And so radon is another element that is a possible indoor air pollutant if those levels get too great inside the home. So again, one of the main things to make sure of is that your home is well ventilated and that your air filtration systems and HVAC systems stay in good working order so that your home stays well ventilated. So that's the key to avoiding indoor air pollution, is knowing what you're burning inside of your house. Don't smoke inside of your house, and make sure your ventilation systems are working up to standards. And so when it comes to our outdoor air, how can we further improve our air quality? Sustainability is the way forward. And what sustainability means is not just thinking about what I'm doing and how it affects me and those around me right now today, but also think about what you're doing today and how it's going to affect the planet in the future. So that's the staple of sustainability. And so one of the things that have been practiced, and it's been practiced more and more over the past 20, 30 years, is the concept of green chemistry when it comes to how we perform experiments in an academic setting in a chemistry lab, how chemical companies that produce chemicals, how they produce chemicals, what they do with their waste, so on and so forth. And so green chemistry is a way of reducing pollution through the design or redesign of chemical processes. So therefore, if we're doing a chemistry experiment that may contribute to indoor or outdoor air pollution, how can we redesign this experiment so that we minimize the effect of air pollution? Same thing with chemical companies. Is there something we can do to change the reaction mechanisms or the design of this experiment so that we're creating less air pollution? And so green processes, they require less energy, they create less waste, use fewer natural resources, and also use renewable resources. And those are some things that make the approaches greener and therefore more environmentally friendly. And so some of the things that have been done recently to initiate more green chemistry principles, things like synthesizing plastics from renewable sources instead of typical fossil fuel derived precursors, and then using paints that have fewer volatile organic compounds, finding cheaper and less wasteful ways to produce products for consumers, limiting or eliminating the use of organic solvents, which have high levels of VOCs, and then removing arsenic from our products, our things like our touchscreens of our portable electronic devices. And so all of those things help to reduce the probability of air pollutions and air pollutants getting into the atmosphere, and they help us use natural resources more effectively and more sustainable. So that brings us to the end of chapter 2. And again, we have a PDF file of a study guide available. And so you're advised to go through all of those topics on the study guide, make sure that you understand all of those concepts. Again, I'm available between now and Sunday night at 11:59 p.m. when your first chapter exam is due by. If you have any questions that you want to ask me, feel free to email them to me, or you can go to the activities tab, discussions. And I have a help, I don't understand the content discussion board set up for you. So if you have some questions about chapter 1, post any questions you have, click start a new thread, and then put in something in the subject tab, and then type your question. And I'll be checking the discussion board this weekend to see if you've posted me any questions there under chapter 1 and chapter 2, or you can just simply email me your question through eLearn email. If you want to set up a Teams meeting with me, I'm available to do that now between now and Sunday as well. So just send me an email letting me know what day, what time you would like to meet with me, and I will make that happen. And so we've got about 10 minutes or so remaining in our class today. And so would you rather I start chapter 3, or would you rather ask me some questions about chapters 1 and 2 that are covered in the exam?
I have a question.
Yes.
Material. So for this part, you said like the first part, the conversion, like that little like mathematical issue, or not issue, but problem would be on the chapter exam. Is the whole part 3 going to be on the chapter 3 or the chapter exam, or is it just like that first part, that first like math problem conversion thing?
Okay, so you're asking, well, conversion of units?
No, I mean, like kind of sort of like that whole thing with the aspirin, like you went through that whole problem.
Okay.
You said that it would be on the exam. Is the rest of that part 3 material going to be on the exam, or does it stop after the problem?
Okay, what concept that was involved in doing this that will actually be on the exam is density.
Okay.
I may ask you a question. I may say, the density of a liquid is 1.11 grams per milliliter. I have 5 milliliters of it. What is the mass of this liquid?
Oh, okay, I got it.
That requires you using the density formula.
Okay, thank you.
And rearranging that mass then would be the volume times the density. So you'll see a question like that on the test. Also dealing with density, you may have a question, and there's a question like this on the math review. And I posted you some math review videos. And if you watch this math review video on density, click open another window, and there's a video on density. I would definitely recommend you watch that video on density. Okay? And it's only about 5 minutes long. Another type of density question that you could be asked So I have a box. That's 6 centimeters in height, 8 centimeters in length, and 5 centimeters in width. And my box has a mass of 50 grams. What is the density of the box? Well, I already know the mass of the box. And we said that density is mass over volume. So I know what the mass of the box is. But what is the volume of the box? Well, the volume of the box is the length times the width times the height. So first I would need to calculate my volume. 8 times 6 times 5. And that gives me 240. Now each dimension is in centimeters. So my units would be centimeters cubed. So when I did my multiplying, 6 centimeters, and each centimeter is to the first power, times 8 centimeters, times 5 centimeters. And when we multiply, our math rule tells us that we need to add exponents. So 1 plus 1 plus 1, that's where I get the 3 from. So now that we know our volume and we know our mass, we can calculate density. And the density is grams per cubic centimeter. 1 cubic centimeter is the same thing as 1 milliliter. So we could say our density is 0.208 grams per milliliter. A milliliter and a cubic centimeter is the same thing. So if you're in the medical field, if you're giving an injection of something, you usually measure out probably how many cc's that you're going to give the patient. The cc stands for cubic centimeters. Which we can also call centimeters cubed. But the medical term is cubic centimeters or cc's. Okay. So you won't be asked anything harder than this about density. You may be asked to calculate the density of a box given the dimensions and the mass, or you may be given the mass and the density of a substance and asked to calculate the volume, or you may be given the volume and the density of a substance and asked to calculate the mass. So mass is density times volume. Density is mass divided by volume. And volume is mass divided by the density. So given either two of these three quantities, you should be able to calculate the third. Any other questions? Well, if there aren't any other questions, we'll end class for today. And remember to go through the study guide, go back through all your notes and recalculate all the problems that we did in class. You may want to just start with a clean copy of the notes and going through each of the problems, referring back to your notes as you study back through all of those problems, and also go back and study your Chapter 1 and Chapter 2 quizzes. And if you go through all of the concepts that I have listed on the study guide, and you understand all those concepts, then you should be fine for the test. So have a good rest of your week. I'll see you in lab either Thursday or Friday. If I don't have you in my lab, I will see you on Monday of next week. And we will start Chapter 3 next week.